Now we will continue with the solubility of solids in liquids. This slide talks about the heat of solution. We have discussed this in previous lectures, but here we want to put more focus on electrolytes or salts since we are discussing them in the next slide. Heat of solution, which is delta H or sometimes called the partial heat of solution, can be defined as the heat absorbed per mole when a small quantity of a solute is added to a large quantity of solution. We mentioned that earlier that a positive value of delta H indicates an absorption of heat, which is an endothermic process, since the solute-solute and solvent-solvent interactions may exceed the energy provided from the solute-solvent interactions. And to complete the solution process, the thermal energy is needed, and it is absorbed from the environment. Now, when delta H is negative, then this indicates evolution of heat, which means an exothermic process. In such exothermic process, the solute-solvent interactions, we called them earlier 1-2 interactions, may exceed both solvent-solvent interactions, which are 1-1 interactions, and solute-solute interactions, the 2-2 interactions. This will result in excess energy produced in the form of heat. Usually, substances with large negative heat of solution are more soluble than substances with small negative heat of solution. However, compounds that have a positive heat of solution may also be soluble, but generally they are less soluble than those that undergo an exothermic process. Also, the spatial arrangement of a solute molecule in a crystal may decrease the movement from the solid phase into solution. Therefore, as a general rule, crystals composed with asymmetrical molecules are more soluble than those that are highly symmetrical. Therefore, amorphous solids are usually more soluble than crystalline counterparts. We have learned earlier that the driving force for dissolution and for all chemical processes is determined by the Gibbs free energy change, which is delta G. Now, the dissolution of salt is understood as a sequence of two processes. The first process or step is the breakup of the ionic lattice of the solid. In this step, the solid ions transfer into gaseous ions without passing through the liquid phase by a process called sublimation. This first step consumes a large quantity of energy, something that by itself would strongly discourage solubility. Delta H of sublimation is positive, so it is an endothermic process. The second step is the attachment of water molecules to the released ions, the process called solvation or hydration. This step releases a large amount of energy, so it is an exothermic process. Thus, the net energy change or delta H total depends on the sum of the two large energy terms. So, net energy could be positive or it could be negative. Each of the previous steps will to some extent be influenced by the size, charge, polarizability of the particular ions, and on the lattice structure of the solid. This large number of variables make it impossible to predict the solubility of a given salt. You can take a look at the figure in this slide to see the net total solubility of some salts. It could be positive or it could be negative depending on the delta H's of the processes of breakup or solvation. Remember that in solvation process usually it occurs by ion dipole interactions. Now, what happens if a very soluble electrolyte, such as ammonium sulfate, is present or added to a solution of non-electrolytes? Ions of highly soluble electrolytes, such as ammonium sulfate, have a marked affinity for water. So, It will reduce the solubility of an electrolyte by competing for the aqueous solvent and breaking the intermolecular bonds between the non-electrolyte and the water. This effect is important in the precipitation of proteins, and this process is also called salting out. We have seen a similar effect when we talked about the gas solubility in liquids. For drugs with ionizable groups, their solubilities in water is affected by the concentration of hydrogen ions in water. We call this the pH. The great majority of drugs are weak electrolytes, weak acids, or weak bases, and therefore they are strongly influenced by the pH of the solution. Acidic drugs such as nonsteroidal anti-inflammatory agents were found to be more soluble in alkaline media and less soluble in acidic media, since the acid remains undissociated in the acidic media and therefore less solvation of water occurs. As we mentioned in the previous slide, the solubility of weak electrolytes is strongly influenced by the pH of the solution. This is highly important to prepare solutions of these weak electrolytes at suitable pH, where they become soluble to achieve maximum therapeutic effects. We can derive equations relating the solubility of these weak electrolytes to the pH of the medium. When a weak acid, for example, is added to water, it will ionize partially depending on its pKa and depending on the medium pH. We have seen this in the ionic equilibria chapter. The ionized fraction is usually much less than the unionized fraction. Hence, the unionized fraction precipitates since most of it is insoluble and is considered as constant and is given the term S0 or S0. For the ionized part, we can determine the amount of ionized species, that is P minus, using the common ionization equations as we saw in the acid-base equilibria chapter. The total solubility, which we term as S capital in this chapter, is a sum of that of unionized and ionized species. So briefly, S total will be equal to P minus plus S0 or S0. Now, using the Henderson-Hasselbalch equation and substituting for ionized and non-ionized concentrations, we can reach to the following equation, which states that PHP minus pKa equals to the log S minus S node divided by S node. Note that S node is the solubility or concentration of unionized species, while S is the total solubility or concentration of the ionized and non-ionized species. Therefore, the difference S minus S node is the solubility or concentration of ionized species. PHP in the above equation is the pH below which the drug separates from solution as the undissociated or unionized acid. The subscript P stands for precipitate. Therefore, we can use this equation to calculate the solubility of any drug that is weak acid at any pH if we know the pKa and S node. From the previous equation, we can say that the solubility of weak acidic drug increases with increasing the pH, which means it becomes more soluble in alkaline pH. This is an example that we can practice on the previous equation, the effect of pH on the solubility of weak acids. In this example, the pH below which sulfadiazine drug will precipitate from solution is required. So we need to know the pH at at which this drug will precipitate or will start to precipitate. What is given in the example is the solubility of the salt, sulfadiazine sodium, that is initially available in the infusion fluid. Also, the solubility of sulfadiazine, which is a weak acid, is given. What we do now is to input all the data in the previous equation, as you see in this slide. And the PHP is calculated to be equal to 8.6. Therefore, sulfadiazine sodium will precipitate as sulfadiazine free acid once the pH gets to 8.6. Note that as the pH gets lower, more sulfadiazine will precipitate accordingly. Similar to the weak acids, we can also derive an equation relating the solubility of weak bases to the pH of the medium. The equation that you see in this slide is derived using Henderson-Hasselbalch equation to relate the solubility of weak bases to the pH of the medium. It is very similar to that for weak acids, except for the ratio of S and S minus S node, where they are flipped over. Note that pKw in this equation minus pKb is basically equal to pKa. So we can say that PHP equals pKa plus log S node divided by S minus S node. All other parameters are similar to those we have seen in the weak acid equation. From this equation, we can say that the solubility of weak basic drug increases with decreasing the pH, which means that it becomes more soluble in acidic media. This slide summarizes the effect of pH on the solubility of weak acids and bases and also on amphoteric species. You can learn from the figure that you see in this slide that the solubility of acidic drug increases with the increase in pH, while the solubility of basic drugs increases with the decrease in pH. Also, you can see that the solubility of amphoteric drug shows a U-shaped solubility curve, where it behaves as a base below certain pH and as an acid above certain pH. Please refer to the end of this handout for more practice examples on the effect of pH on solubility.